Welcome back, learner, to another deep dive. I know you're all about maximizing your knowledge without getting bogged down in the weeds, and that's what we're here for. Today, we're tackling determinants.
Yeah, determinants. Sounds kind of mathy, right? But trust me, this concept is way more versatile than you might think. It pops up everywhere from engineering and all sorts of sciences to economics and even social sciences. The sources you sent over give us a really good look at determinants up to the third order, all using real number entries.
Perfect. So what's the mission for today's deep dive? What are we trying to unpack here?
Well, today we're aiming to give you a solid understanding of what exactly determinants are, how you actually calculate them, and perhaps most importantly, why they matter so much across all these different fields. We'll cover the definition, walk you through the steps for calculating them for different size matrices, look at some really useful properties they have, and then tie it all back to real-world applications.
Love it. And just to get your brains warmed up, think back to high school algebra, when you first learned about solving systems of two linear equations, those pairs of equations like a1x plus b1y equals c1 and a2x plus b2y equals c2. Remember that rule for when you get a single unique solution? It's often stated as a1d2, a2b1, a0.
Exactly. And what's super interesting here, learner, is that this expression, a1b2, a2b1, is actually the determinant of the coefficient matrix for those equations, which would look like a1b1, a2b2. So you can kind of see right off the bat that a non-zero determinant is a huge clue about whether you'll find that single unique solution.
Okay, so let's back up a sec. What exactly is a determinant?
All right, so formally speaking, a determinant is a number, and for our purposes today, we're just going to stick to real numbers, but it could be other types of numbers that we associate with every square matrix.
Square matrix being the key here, right?
Right, same number rows and columns. And when we talk about the determinant of a matrix, let's say our matrix is called A, you might see it written in a few different ways, like you might see A, dA, or even the Greek letter delta, just so you know. Even though it sometimes looks like those vertical bars we use for absolute value, it's a whole different concept.
Okay, got it. So let's start with the simplest possible case. Like, what if we just have a one-by-one matrix?
Easy peasy. If your matrix A is just a single number in those square brackets, like A is A, then its determinant A is just that number itself, A. Simple as that.
Okay, that makes sense. So how about two-by-two matrices? Things get a little more interesting there, right?
Yeah, for a 2 by 2 matrix, let's say we have matrix A with elements A11, A12, A21, A22. The determinant, whether you call it dA or A, is found by taking the product of the elements on that main diagonal, so A11 times A22, and then you subtract the product of the elements on the other diagonal, A21 times A12. So the formula looks like this: A11, A22, A21, A12. Kind of think of it as a crisscross multiplication and a subtraction.
Okay, I think I'm following. Crisscross, subtract.
Ah.
Easy. Does the source material have any examples to help illustrate this?
Yeah, for sure. So example 1 wants us to find the determinant of 2, 4, minus 1, 2. So using our crisscross rule, we do 2 times 2 minus 1 times 4, which is 4 minus 4, which simplifies to 4 plus 4, giving us a determinant of 8.
Got it. So that's how you find the determinant of a two-by-two matrix. All right, let's step it up another notch. How about determinants of three-by-three matrices?
Okay, so 3 by 3 determinants, they get a bit more complex, but the basic idea is still to break them down into smaller pieces that we already know how to handle, those 2 by 2 determinants. This process is called expanding the determinant. The really cool thing is that you have some flexibility here. You can actually choose to expand along any of the 3 rows, R1, R2, R3, or any of the 3 columns, C1, C2, C3. No matter which row or column you pick, you'll always end up with the same value for the determinant.
Okay, so I have choices. Interesting. Can you break down the expansion along the first row, R1, step by step?
Yeah, absolutely. So let's say we have a 3 by 3 matrix A that looks like this: A11, A12, A13, A21, A22, A23, A31, A32, A33. First, we take that first element of R1, which is A11, and multiply it by a sign factor. The sign factor is 1 minus 1 raised to the power of 1 plus 1, because it's in the first row and first column. And since 1 plus 1 is 2, minus 1 a point just gives us positive 1. Then we multiply this whole thing by the determinant of the 2 by 2 matrix that's left when we kind of like mentally cross out the first row and the first column.
Yeah.
So we're left with A22, A23, A22, A33.
Okay, so the first term in our expansion is like minus 1 plus 1 times A11 times the determinant of A22, A23, A23.
Okay, got it. So what's next?
Now we move on to the second element of R1, which is A12. Multiply this by minus 1 to the power of 1 plus 2, since it's in the first row, second column. 1 plus 2 is 3, so minus 1 gives us negative 1. And then, just like before, multiply this by the determinant of the 2 by 2 matrix that we get when we delete the first row and second column. So we're left with A21, A23, A31, A33. All right, so the second term is -1, 1 plus 2, times A12 times the determinant of A21, A23, A31, A33. And that simplifies to negative A12 times A21, A33 minus A31, A23 because of that negative sign we get from the odd power.
Perfect. You got it. And finally, the third element in the first row, A13, is multiplied by -1 to the power of 1 plus 3, first row, third column. 1 plus 3 is 4, which means -1 is just +1. Then we multiply by the determinant of what's left after removing the first row and third column, which is A21, A22, A31, A32.
So that third term would be -1 plus 3 times A13 times the determinant of A21, A22, A31, A32, which simplifies to A13 times A21, A32 minus A31, A22.
Exactly. And the last step, we simply add these three terms together to get the determinant of our original 3 by 3 matrix A. So det A equals A11 times A22, A33 minus A32, A23, minus A12 times A21, A33 minus A31, A23, plus A13 times A21, A32 minus A31, A22. I know it looks a little complicated at first, but it's really just a systematic way of breaking down a 3 by 3 problem into those smaller 2 by 2 determinant calculations.
Right. Okay, that's actually not as bad as I thought. So we basically just choose a row or column, break it down, and then use what we know about 2 by 2 determinants.
All right.
And it doesn't matter which row or column we choose.
Nope, not at all. And as a bonus tip, check out Remark in the source material. It suggests picking the row or column with the most zeros for easier calculations.
Yeah.
Makes sense, right? If you're multiplying by 0, that whole term just vanishes, which simplifies things. Less work for the same answer. Always a good thing.
Totally. Less work is always good. What about that net if 1I plus j term? Is there a simpler way to think about that?
Yeah, for sure. Remark 2 reminds us about that sign factor. Basically, you multiply by +1 if the sum of the row and column indices I plus j is even, and by mag of 1 if it's odd. You can kind of visualize it as a checkerboard pattern of pluses and minuses across the matrix.
Ooh, like a checkerboard. I like that. Visuals always help. Okay, so does the source have some examples of putting all this into practice?
Absolutely. Let's take a look at example 3. We need to find the determinant of 1, 2, 4, -1, 3, 0, 4, 1, 0.
Anything jump out at you about this matrix?
We'll take a look at the third column, C3. 2 zeros there, bingo. Let's expand along C3. Makes things way easier. So we've got elements 4, 0, and 0. For the first element 4, it's in the first row and third column, so I1, J3. That means I plus j equals 4, which is even, so we use a +1 sign. The 2 by 2 determinant we get after deleting that row and column is mod equals 1, 3, 4, 1. That gives us mod equals 1 times 1 minus 4 times 3, which is mod equals 1 minus 12, or minus of 13. So our first term is +1 times 4 times mod equals 13, which equals mod to 52.
All right, and the next two elements are zeros, so it doesn't matter what the signs are, they're both going to zero out those terms, right?
Exactly. So the total determinant is just mod equals 52. Way simpler than expanding along a row or column without any zeros.
So much simpler. Okay, what about example 4? What's that one look like?
Example 4 gives us a determinant with some trigonometry in it. 0, sinal akos, ox of sinat. 0, sinat cosmos, sinanite. 0. Ooh, trig. Let's see how this one plays out. The source shows the expansion along R1. So the first element is 0. And of course, anything times 0 is just 0, so that term vanishes. The second element is sinat, and it's in the first row, second column. So I plus j is 3, which is odd. That means we get a negative sign. The minor 2 by 2 determinant is sinat cos pol, 0, which gives us a sin times 0 minus psi pos times sinat, which is sinat cos pic. So that second term becomes sinat cos pic, which is sinat cos pic.
Okay, I'm following. So then the third term, that's a cos ob, first row, third column, so ai plus j equals 4, which is even. So we're back to a positive sign. The minor determinant is sin cos ob spro, which will tell us that to be sin times sin cos minus cos bat times 0, which is sin a sin back. So the third term is acos as pas bat times sin a sin back, which gives us acos as sin a sin.
Yep. So putting it all together, the determinant is 0 plus sin as sin cos minus cos sin a sin back, which is just 0. So
Yeah.
even with the trigonometry, we carefully expand and we find out the determinant is 0.
Perfect. It all zeroes out. Nice. All right, ready for another example?
You bet. Example 5 asks us to find the values of x that make the determinant of 3x(3) equal to the determinant of 2, 4, minus 1, 2. We already figured out earlier that the second determinant is 8. For the first one, we can use our 2 by 2 determinant rule. That gives us 3 times 3 minus x times x, which is 9 minus x squared. So we need to solve the equation 9 minus x squared equals 8.
All right, so if we rearrange that, we get x squared equals 9 minus 8, which is 1. Take the square root of both sides, and that gives us x equals plus or minus 1.
Exactly. So those are the values of x that make those two determinants equal. Makes you appreciate how even a single variable can change the whole game, right?
Absolutely. Okay, so we've seen how to calculate these determinants. Now, what about some tricks to make life a little easier? Any shortcuts or special properties we should know about?
You bet. Let's dive into some of the properties of determinants. This is where things get really powerful, learner. These properties give us these cool shortcuts and insights into how determinants work without always having to crunch through the whole expansion process. The source says these properties hold for any ordered determinant, but for our deep dive, we'll just focus on those of order 3.
Sounds good. So, what's the first property?
Property 1 is all about a matrix and its transpose. Remember, the transpose of a matrix is what you get when you flip it over its main diagonal. So rows become columns and columns become rows. What property 1 says is that the determinant's value stays the same even when you do this flip. So dt equals bt, where A represents the transpose of A.
Okay, so flipping the matrix doesn't change its determinant. Does the source go into any detail on why that is?
Yeah, they actually take a general 3 by 3 matrix, find its transpose, and then expand both determinants. They expand along the first row for the original matrix and the first column for the transpose, just to show that you end up with the exact same expression. And they use that notation psi to show that swapping of the ith column and the ith row.
Okay, so they show it algebraically. What about numerically? Do they have any examples with actual numbers?
They do. Example 6 gives us a concrete example of error for property 1. They take this determinant, which is 2, -3, 5, 6, 0, 4, 1, 5, -7, and they calculate it to be -28. Then they find the transpose of this matrix, and they calculate its determinant as well, and what do you know, it's also -28. So property 1 holds up numerically.
-28 both ways. Cool. All right, what's property 2?
Property 2 tells us what happens when you swap any two rows or any two columns of a determinant. It says that if you do this swap, the sign of the determinant flips. So if the original determinant was positive, it becomes negative, and vice versa. They use RR to show the swapping of rows and CEO for swapping columns.
So one swap equals one sign flip. Pretty straightforward. Does the source show this algebraically as well?
You bet. They use a general 3 by 3 matrix to show how the sign changes when you swap rows or columns.
And any numerical examples for property 2?
Yep. Example 7 uses the same determinant from example 6, that 2, -3, 5, 6, 0, 4, 1, 5, -7, 1, which we know has a determinant of -28. This time, they swap rows R2 and R3, and the new determinant they get, Ne1, is 28, which is indeed the negative of the original -28.
Okay, that makes sense. So far, so good. Property 3, what have we got?
Property 3 is a really helpful one for simplifying things. It says that if any two rows or any two columns of a determinant are exactly the same, meaning all corresponding elements are equal, then the determinant is 0.
Wait, so if two rows or two columns are identical, the determinant is automatically 0.
Yep. Think about it this way. If two rows are giving you the same information, they're not really independent of each other. And that lack of independence leads to a determinant of 0.
I never thought of it that way. Does the source offer any proof of that?
They do. They explain that if you swap the identical rows or columns, the matrix itself doesn't change, right? So the determinant shouldn't change either. But according to property 2, swapping two rows should change the sign of the determinant. The only number that stays the same when you change its sign is 0.
Oh, that's a clever way to think about it. Do they have a numerical example to show this?
Yeah, they give example 8, where it is 3, 2, 3, 2, 2, 3, 3, 2, 3. Notice that the first and third rows are identical, and if you calculate the determinant, you'll find it's indeed 0.
Makes sense. Okay, what's next on our list of determinant properties?
Property 4 has to do with multiplication. It says that if you multiply an entire row or an entire column of a determinant by a constant, let's call it k, then the value of the whole determinant also gets multiplied by k.
Okay, so multiplying a row or column is like multiplying the whole determinant. Pretty intuitive. How do they show that?
The source shows this with a general 3 by 3 determinant. They multiply its first row by k, and then they factor out k from the entire determinant expression, showing they are equal.
Okay, I can see how that works. Anything else noteworthy about property 4?
Yeah, Remark points out that this means if you see a common factor in all the elements of a row or a column, you can just pull that factor out in front of the determinant. Simplifies things.
Ooh, another good trick to remember. Any other remarks?
Yeah, Remark 2 is interesting. It says that if two rows or two columns are proportional, meaning one row is just a constant multiple of the other, then the determinant will always be 0. This makes sense because you could factor out that constant, which would leave you with two identical rows. And we know from property 3 that a determinant with identical rows is 0.
Right, right. Proportional rows are basically just hidden identical rows. Any example of that?
Example 9 illustrates this with the determinant 102, 18, 36, 1, 3, 4, 17, 3, 6, which is 0, because the first row is exactly 6 times the third row.
Cool. So that's property 4, all about scaling a determinant. What's up next?
Property 5 deals with determinants, where some or all elements of a row or column are actually sums of 2 or more terms. It basically says that you can split up that determinant into the sum of 2 or more determinants.
Okay, so if I have a row with sums, I can break up the determinant. Can you give an example?
Yeah, so the source gives an example where the first row has elements that are sums, and they show how you can split it into 2 separate determinants that have the same other rows.
Okay, that makes sense. Do they show why this works?
Yep. They expand all the determinants along that first row with sums and show that both sides of the equation are the same algebraically.
Okay, cool. Any numerical examples?
Yeah, example 10 uses this property in a clever way to show that this determinant, a plus x, b plus y, c plus z, a, b, c, x, y, z, has a value of 0. They split it into 2 determinants, and in both of those, you end up with either the first and second rows proportional or the first and third rows proportional, which we know from property 4 and 3 means the determinant is 0.
Oh, that's sneaky. So we're up to property 6. What's that one all about?
Property 6 is probably the most useful one we've got. It says that if you add a multiple of one row or column to another row or column, the value of the determinant doesn't change at all. This is written as year plus krj or CEC plus kcj.
So you can add multiples of rows and columns together without affecting the determinant. That seems pretty powerful. Why is that so useful?
Remember how we said picking a row or column with lots of zeros makes calculations easier? Well, property 6 lets you actually create those zeros.
Oh, I see. You can manipulate the determinant to make your life easier. Does the source explain why this works?
They do. They show it using a general 3x3 matrix. They perform the row operation R1 plus KR3, use property 5 to break it up, and then use the fact that determinants with proportional rows are 0.
Clever. Any important points to keep in mind when using this property?
Yeah, there are a couple of remarks about that. Remark says, be careful not to accidentally multiply a row by a constant directly. Like, don't do re. It has to be the addition of a multiple of another row. Got it. No direct multiplication, only addition of multiples. What about remark 2? What's that one about?
Remark 2 cautions about doing multiple of these row operations at the same time. Like if you modify a row, don't use that same row in another operation within the same step.
Okay, I can see how that could get messy. So use property 6 strategically. Does the source have any examples that show how we can use this property effectively?
Definitely. They have a bunch of examples from example 11 through 16 that really highlight how we can strategically use these properties to evaluate determinants and even prove some pretty cool identities without having to resort to brute force expansion every time.
Like what kind of identities? Can you give me a taste?
Sure. For example, 11 shows how to prove that a certain determinant is equal to a row just by using these row operations. Example 12 shows how to prove that another determinant is 0 by creating proportional rows.
Okay, so you can really manipulate these determinants to make things work out nicely. What about examples 13, 14, 15, and 16? So, example 13 shows how to evaluate this kind of complicated determinant to get A minus B times B minus C times C minus A by strategically introducing zeros and factoring. Example 14 similarly proves that a determinant is equal to 4ABC. Example 15 gives a more involved determinant equation and uses these properties to figure out that 1 plus I psi z equals 0 under certain conditions. And finally, example 16 proves this quite complex determinant identity just by manipulating rows and columns.
Wow, those sound pretty impressive. Seems like mastering these properties is key for efficiently working with determinants, especially as the matrices get bigger and more complex.
Absolutely. It's all about working smarter, not harder.
Love it. Okay, let's shift gears a bit and talk about these things called minors and cofactors. What are those all about?
So minors and cofactors might sound like minor players, but they're actually super important for understanding the structure of a determinant and are crucial when you're trying to find the inverse of a matrix, which we'll get to in a bit.
All right, bring on the minors and cofactors.
Okay, so definition 1 tells us that the minor of an element A in a determinant is just the determinant of the smaller matrix you get when you remove the row and column containing A.
Mm-hmm.
We represent the minor of A as me, So if your starting determinant is of order n, meaning it's an n by n matrix, then the minor will always be a determinant of order n1. It's one size smaller.
Okay, so it's like zooming in on a smaller part of the matrix. Can you give me a concrete example?
Definitely. Let's look at example 19. They give us this determinant 1, 2, 3, 4, 5, 6, 7, 8, 9. And they ask us to find the minor of the element 6. So 6 is in the second row, I2, and third column, J3. So if we delete the second row and third column, we're left with a 2 by 2 matrix. 1, 2, 7, 8. The determinant of this minor, M23, is 1 times 8 minus 7 times 2, which is 8 minus 14, which equals -6.
Okay, so the minor is just the determinant of that smaller matrix. Easy enough. Now, what about cofactors? How do those fit in?
Definition 2 introduces the cofactor. The cofactor of an element I, written as I, is just the minor we talked about, multiplied by either +1 or making 1. The sign is determined by the position of the original element in the matrix. It's that -1 I plus j term again, which gives us that checkerboard pattern we talked about before. Plus, minus, plus in the first row, then minus, plus, minus in the second row, and so on.
So it's the minor with a plus or minus sign, depending on its location. Makes sense. Does the source have any examples of how to find cofactors?
Yeah. Example 20 walks us through finding all the minors and cofactors of a 2 by 2 determinant, 1 minus 2, 4, 3. So for the element A11, which is 1, if we get rid of the first row and first column, we're left with just 3. So the minor M11 is 3. And since it's in the first row and first column, I plus j is 2, which is even, so the cofactor A11 is positive 1 times 3, which is just 3.
Okay, makes sense. What about the other elements in that 2 by 2 matrix?
All right, so for A12, which is -2, the minor M12 is 4, because that's what's left when you remove the first row and second column. But it's in the first row, second column, so I plus j is odd, meaning the cofactor A12 is -1 times 4, which is -4. For A21, which is 4, the minor, M21, is -2, and because I plus j is odd, the cofactor A21 is -1 times -2, which is +2. And lastly, for A22, which is 3, M22 is 1, and since I plus j is even, A22 is just +1.
Okay, so basically you just got to keep track of the signs based on the row and column of each element. Got it. Now, how do these minors and cofactors relate back to determinants?
Here's the really cool part. You can actually find the determinant of a matrix by taking the sum of the products of the elements of any single row or column with their corresponding cofactors. So like the source shows, if you expand along the first row, you'd have A11 plus A12, A12 plus A13, A13. It gives you another way to think about calculating determinants, especially for those larger ones.
So you're saying we can use cofactors to break down the determinant.
Yeah.
Interesting. Is there anything tricky about this method?
Well, here's something really important to remember. If you multiply the elements of a row or column by the cofactors of a different row or column, that sum will always be 0. The source gives this example. A11, A21 plus A12, A22 plus A13, A23 equals 0. Think about why that might be. You're basically calculating the determinant of a matrix that has two identical rows, in this case the first and second, and we know from property 3 that a determinant with identical rows is always 0.
Oh, that's right. I see the connection now. So cofactors from a different row or column always lead to a 0 determinant. Does the source have any examples of that?
Yep, example 22 drives that point home. It uses this matrix, 2, not of the 3, 5, 0.6, 0, 4, 1, 5, matrix 7. They find all the minors and cofactors for its elements and then show that A11, A31 plus A12, A32 plus A13, A33 equals 0. So it proves that multiplying the elements of one row by the cofactors of a different row results in 0.
Perfect. That makes a lot of sense. So cofactors seem pretty important. Where do they come in handy?
Well, now we're getting to one of the most important applications of determinants, finding the inverse of a matrix. But before we go there, we need to understand something called the adjoint of a matrix.
The adjoint of a matrix. Okay, I'm listening.
All right, definition 3 says that the adjoint of a square matrix A, written as AJ is the transpose of the matrix of its cofactors. So you calculate all the cofactors, put them into a matrix, and then take the transpose of that matrix. Remember, transpose means swapping rows and columns.
So find all the cofactors, make a matrix, and then flip it. Got it. What does the source show about this?
The source gives us the formula for the adjoint of a 3 by 3 matrix in terms of its cofactors. And then example 23 gives us a 2 by 2 matrix, A equals 2, 3, 1, 4, and they walk us through finding its adjoint. They first calculate the cofactors, which are A11 equals 4, A12 equals 1, A21 equals 3, and A22 equals 2. Then they arrange these into a matrix, which gives us 4, meta 1, negative 3, 2. Finally, they take the transpose, giving us the adjoint of A as 4, negative 3, negative 1, 2. There's even a shortcut for 2 by 2 matrices. You can just swap the main diagonal elements and change the signs of the other two.
Ooh, shortcuts are always nice. Okay, so now we know about adjoints. How does this all relate to inverses?
Well, Theorem 1, which the source just states without proving, gives us this really important relationship between a matrix, its adjoint, and its determinant. It says that A, adj A equals AI. And then here's the identity matrix, which is basically like the matrix version of the number 1. This theorem is the key to unlocking how to find the inverse.
Okay, so that theorem connects the matrix, its adjoint, and its determinant to the identity matrix. Interesting. So are we ready to talk about inverses?
Almost. Definition 4 introduces this concept of a singular matrix. It says a square matrix A is singular if its determinant A is 0. Definition 5, on the other hand, defines a non-singular matrix as one whose determinant is not 0. For instance, the source shows a 2 by 2 matrix whose determinant is 0, making it singular, and another 2 by 2 matrix whose determinant is -2, making it non-singular.
So singular means determinant is.